All right, so let's go ahead and review continuity condition again. So we have two kinds of continuity. One is at a point, and we already did that in the last video. So it's only continuous when three conditions are met. First one, f of c is defined. So there is actually a number. Number two, the limit as x goes to c of f of x exists. And then you do need to prove that it exists by saying the left hand side of c is the same as right hand side of c is the same. I mean, if those two things are the same, then you can safely conclude that the limit as x goes to c is the same number. And then the third thing is that then you have to prove that both of them are equal to each other. Then the function is continuous at that point. The second thing is to prove that there is a continuity on an open interval. Closed interval. Closed interval. Closed interval AB. So what does that mean? So closed interval AB, meaning that the two are closed ends. And then if we're proving that it is a continuous function, then what we want to do is just show that the limit as x goes to a positive, so slightly to the right of a, of f of x is equal to f of a. So we're basically proving that the left hand endpoint has an endpoint. And then the limit as x goes to b from the negative side, that is here, f of x equals f of b. And that just helps us prove that the two endpoints of the closed interval exist, and then whether it is continuous everywhere in the middle, that we can't quite prove it. We can only talk about whether the function has a discontinuity based on your understanding of that function, of that parent function, or like the transformation of that parent function. So you kind of think of it in a way, you can't quite prove continuity. You can show that there is no discontinuity. Does that kind of make sense? You can't tell them that it's continuous every single point, because then you will have to show every single point, but you can tell them that there is nowhere that has a discontinuity. Anyways, I will kind of show you. Okay, so let's go ahead and try these questions. Determine whether each function is continuous at a given value. Classify the type of discontinuity. So they're saying that if they're, first prove whether it is continuous or not. If it's not continuous, what kind of discontinuity does it have? So let's try this one. This function, what's going on at 2? Okay, so we need three things to prove continuity. First, it has to be defined at that number. So put 2 in, we get 2 squared minus 2 over 2 minus 2. That is 0 over 0, indeterminate. Please make sure you do write that. Do not write 0 over 0. Make sure you write indeterminate. All right, so that's kind of a problem. Okay, next, what's the limit? Limit as x goes to 2 from the negative side. We already know that it's not going to be defined at 2. In fact, it gives us a 0 over 0. So if we want to find a limit, we're going to do the algebraic way. In this case, we can factor. So limit as x goes to 2. We can, yeah, do this. Okay, so factor, we get x minus 2 times x plus 1 over x minus 2. Then that cancels. And then we get limit as x goes to 2 minus of x plus 1. And that's equal to 3. We can perform the same thing for x goes to 2 from the positive side, but we're going to get the same thing because it's the same process. So then we can say that there is a limit. The limit is 3. So limit 2 minus of f of x equals limit 2 plus, and then that's equal to the limit at 2, which is 3. And then the third statement is that the limit as x goes to 2 is not equal to f of 2. So therefore, it's not continuous at x equals 2. Okay, please make sure you do write everything out, especially this x equals 2. Don't just write 2. It's very ambiguous what you mean. Now, the last question it asks is, what kind of discontinuity does it have? If it has a 0 over 0, you can most likely safely assume that it's a whole, especially when it's a rational function with polynomial like that. You can pretty much safely assume it's a whole. So then a whole means that it's a removable discontinuity. All right. Let us, or let you try this one. H of x equals to piecewise. This same function if x is not equal to 2, and 1 if x is at 2. Is it continuous at 2? And then if it's not, what kind of discontinuity does it have? Alright, so let's go ahead and try this one. So number 1, what is f of 2? 1. It tells us it's 1. So if it's not equal to 2, then use the first function. If it's equal to 2, then use 1. Number 2, what is the limit? Limit as x goes to 2 from the negative side. That is limit as x goes to 2 from the negative side of, and then we factor that one. So again, same as before. And then that cancels, so we get limit as x goes to 2 from the negative side of x plus 1, which is 3. And then we can, it's the same statement as before, so we can say that it's the same. Make sure you do write this limit out every single time, okay? Don't just write limit as x goes to 2 plus, and then without the f of x, that makes no sense. And then that's equal to limit as x goes to 2, f of x, and all that is equal to 3. And so the third thing is limit as x goes to 2, f of x is not equal to f of 2. Therefore, it's not continuous at x equals 2. Then what kind of discontinuity does it have? It is still the same. It's a removable discontinuity. It's just that there is an extra point on the top, but then it's still called a whole with this kind as a removable discontinuity. Okay, let's try another one. This one, another piecewise. Go ahead and pause the video, give this a try. All right, 3 conditions. F of 0 is 1. Number 2, what is the limit as x goes to 0 from the negative side? From the negative side, we are looking at this function 1 over x squared. We know that it is undefined at 0, but what's going on if you're getting close to 0 from the negative side? Close to 0 from the negative side, we're going to say something like negative 0.1, right? So 1 over negative 0.1 squared is 1 over 0.01, which is 100. So essentially it is the smaller, the closer we get to 0 minus, we can kind of go crazy on this, square it, which is going to give us even more zeros, which we're going to get this. So what it's saying is that we're just basically getting closer and closer to infinity. And then if we do the same thing with x goes to 0 from the positive side, we're going to see the same thing too, right? We're just putting it as a positive number, but it's squared, so it doesn't really matter. So eventually it's saying it's infinity as well. So both sides are going to infinity. Does that mean the limit exists? No. Remember, we said infinity is not a limit, so the limit does not exist. So limit as x goes to 0. I'm sorry, I keep writing f of x. It's not f. It's g. Sorry about that. G. G of x does not exist. Since the limit does not even exist, we can already conclude that it's not continuous. And then what kind of discontinuity does it have? So both sides of 0 are going to infinity, so we can pretty much clearly say that this is a infinite discontinuity. Now, if we were to look at this graph, which interval is the graph continuous? Which interval is the graph continuous? This is, we're going to assume the two ends keeps going. So the graph keeps going on two ends. And so if you're talking about where is the graph continuous, on which interval, on which x interval, pretty clear. This part is continuous up to -5, and then at -5 it's not continuous, right? So then we can say that it's continuous from -infinity to -5, not including -5 because there is a hole. And then at -5 to 2. So -5 to 2, not including 2. Please make sure that you don't just assume that you can connect those. Actually, especially in this case, gonna kind of show you. Especially in this case, here. This turn doesn't really matter. It keeps going. So then from 2 to infinity, it's continuous. But see here how it's, we're repeating 2, but we can't assume that it will connect that 2 because there is a hole. And just because 2 shows up twice does not mean you can connect the intervals together, because the interval could be discontinuous, especially it's indicated by the parentheses, meaning that it's not supposed to be connected. So please be careful of that. So it's continuous at these 3 intervals. Now let's kind of think about your parent functions. So we learned 12 parent functions last year. So you're going to kind of ask yourself, which functions, kind of to your knowledge, are continuous everywhere, and which functions have discontinuity, and where is it actually continuous? So if the function is discontinuous, where is it continuous? If you don't remember your parent function, please kind of look at your notes from last year. All right, so let's look at it. continuous everywhere, f of x equals x, right? That's the linear function, it's always continuous. F of x equals x squared, f of x equals x cubed, f of x equals square root x. Now you might say square root x does not go on forever. Yes, it doesn't go on forever, but for wherever it actually exists, it is continuous. F of x, the logistic function. I don't know if you remember, that's the function that looks like this. And then we have the exponential. And then the log x, whether that is log base n of x or that is the natural log x, both of them are continuous. And again, it is only continuous on its domain, meaning whatever it's defined, you hopefully remember that the function looks like this. So then there is an asymptote there, but then from where it is going, it is continuous. Okay. We also have the absolute value x, sine x, and then we have cosine x. So where is it? Which function has this continuity? F of x equals 1 over x, the reciprocal function. So then where is it continuous? Well, anywhere besides 0. And then this next one, this one's kind of we don't talk about very much kind of function. The integer function, or the greatest integer function. This is called the greatest integer function. So if you remember, it basically is something like this. You're saying, let's say that you start from 0 and then you want to go up to 1, and then you kind of pick numbers in between. Greatest integer function means that whatever the x is, the y value will only be the previous integer that it has passed from the left to right. So if you are an x value and you are 0, then the biggest integer that you just passed, or actually you're standing on, is 0. If you're an x value that's 0.1, then the biggest integer that you had just passed from left to right is 0. Okay? If you're 0.5, then the biggest integer you had just passed is 0. If you're 0.7, again, it's 0. And then actually you can go all the way up to, like, I don't know, 0.999 forever. But then the biggest integer you had just passed is still just 0. Until you get to 1, then you become 1. And so when you graph this, let's say this is 0 to 1. 0, it is just 0. 0.1 is still 0. 0.5 is still 0. 0.7 is 0. 0.99999 is still 0 until you get to 1. Then you become 1. And so here we're going to put an open circle because we're saying no matter what x value you get to that is slightly smaller than 1, your actual y value is still 0. So this is kind of the greatest integer function, and it just keeps looking like that. So then this function is discontinuous. It has jump discontinuity. Where is it continuous? Basically, you want to say something like 0 to 1, 1 to 2, 2 to 3, and so on.